you doing, Dr. Rob?
Good, how are you? How was your break?
Short and sweet.
Yeah.
How'd you fix it? No. Yes. No, I didn't want to. First time was lovely.
Did I miss anything in the Yeah, I remember that. I didn't know if it's trying to do it.
Hey, Taylor. Follow me on my truck. I'll give you all the way up. Because I have like every single one except this one. Sweet. They're all yours. They're not bad. They're 9s and 10s. So.
Yeah, no, and you put like no effort into the first one. Like if it's gonna be that easy, shit. They're out on here.
You just said answer the questions, so I answered the questions. Paul, you know how Josh is a grammar Nazi?
Oh, yeah, big time.
I had him correct our papers last night.
Oh, he Tuesdays me, but
He's poor.
he takes me.
On Brides, he's like, he had a different font. He's like Arial, and he had to listen to other. He said possibly this. He said, really? He said, go to freshman. Like, for standards. And then, somebody else he said something like, let your hair down, be wild for once, use a conjunction. Like that.
Oh, he ain't gonna let you slide with anything.
No, and I'm glad because it sounds better. Oh, I'm sure.
Okay, so good morning everyone. So last time we discussed, we're getting closer to, understanding the slope deflection method. So the slope deflection method is based on the slope deflection equation. That's what we did during the previous lecture. We were trying to derive this equation, what we were doing to. You're not required, to memorize or know this derivation, okay? But I derived it for you so that you understand what each term means, okay, and where it comes from. So if you have a number like this, the moment at the ends comes from the slope deflection equation. It's 4EI divided by L multiplied by theta A plus 2EI divided by L multiplied by theta B minus 6EI divided by L squared delta. Delta is the differential deflection between point A and B plus the fixed end moment at A. Okay? So this is the slope deflection equation. Slope of two different not two different equations. This is one equation, one time written at A and one time written at. So it's the same equation. It's not any, two different equations. It's just the same equation. And we mentioned that the sign rule, any moment of rotation would be clockwise. That will be positive. For deflection that leads the member to rotate in a clockwise direction, that's positive as well. So, and the kinematic degrees of freedom, those are the unknown deflections and rotations that you need to know in order to use the slope deflection equation, okay? And here we mentioned something about, rules of finding the kinematic degrees of freedom, and we took some examples on calculating those. So today, we can start using the slope deflection equation to solve, okay, indeterminate structures. What do I mean by solving indeterminate structures? Finding the internal forces in indeterminate structures, okay? Drawing the bending moment diagram, drawing the shear force diagram in indeterminate structures. So how to use this slope deflection equation and what we learned so far to find the internal forces in indeterminate structures. The first step, okay, you break the structure down into individual members. And find the kinematic degrees of freedom all, both ends of each member. So you find what are the kinematic degrees of freedom in your structure. And then the second step, okay, you would write the slope deflection equations for the two ends of each member. So like let's say you have a member AB like this, so you write MA. This is the slope deflection equation again. It's 4EI divided by L. L is the length of that member. EI is the modulus of elasticity multiplied by the moment of inertia of that member AB multiplied by theta A. So we're talking here about moment at point A. So this is theta A. Okay? Plus 2EI divided by L multiplied by theta B, the other end or the far end of the member, minus 6EI divided by L squared delta plus fixed end moment AB. And then you write it at the other side. You write the same equation at the other side of the member, at the point B. So it's 4EI divided by L, but now it's theta B plus 2EI divided by L, theta A, minus 6EI divided by L squared, delta, plus fixed end moment dA. The book, okay, rearranged this equation and write it in a different way. So just to, if you go through the textbook, I just want to write it to you as the textbook write it, but I'm going to use it in that form that I just wrote it right now. So after rearrangement, the book write it like this. Just one equation, MN. N is the near point of the member where you're writing the equation. And then taking 2EI divided by L as a common factor here, you have 2 theta as at the near end plus theta as at the far end of the member minus 3 psi plus the fixed end moment at the near end of the member. Okay? So N here stands for the near end of the member. F stands for the far end of the member. And psi here is the slope of the member, which is delta divided by L. Okay? The angle of the slope due to this delta. So Again, here, the first step, you break down the structure into individual members and find the kinematic degrees of freedom, and then you write the slope deflection equation at the end of at the two ends of each member, okay? This is the slope deflection equation. And then after this step, okay, you don't know the kinematic degrees of freedom yet. You just wrote those equations, but the kinematic degrees of freedom are unknown. You need to find them. So you need to find those kinematic degrees of freedom. You're going to use some equations of equilibrium to find the kinematic degrees of freedom. So from the equations of equilibrium, calculate the unknown degrees of freedom. Okay? Once you find your unknown degrees of freedom, the kinematic degrees of freedom which are unknown, you back substitute into the slope deflection method. Yes?
Can you scroll back up?
So you substitute back, substitute the calculated values of the degrees of freedom into the slope deflection equations to find the internal moments. So here in the second step we had the fixed end moments, okay, in the slope deflection equations. Where would you get those fixed end moments? From the back of your book. So the fixed end moments, you either memorize them or get them from the back of the book. So the fixed end moments in step 2 can be found from the table at the back of the book. So those are the steps, okay, of the slope deflection equation or the slope deflection method. Let's apply those steps now, okay? Let's solve some examples here. And using the slope deflection method. So example 11.1. So example 11.1, we have this beam A, B, C. The length is here. Remember, AB is 8 meters long, BC is 6 meters long. On member BC, there is a triangularly distributed load, linearly varying load here, with an intensity of 6 kilonewtons per meter at point C. Okay? And we're given that EI, instead of given the value of EI, it's given that EI, the value of EI is constant. So for member AB, for member BC, they have the same EI value, the same modulus of elasticity, the same moment of inertia. Okay? And we're required to calculate or draw the internal force diagrams. The shear force diagram and the bending moment diagram for this beam. So the thing is, if you try to draw the shear force diagram, the bending moment diagram, using what you learned in structure analysis 1, you're not going to be able to do it. Just applying the equations of equilibrium to find the reactions. How many reactions do you have here? 7 reactions. 3 at A, 3 at C, because those are fixed supports, and 1 at point B, because that is a roller support. So you have 7 reactions. And how many equations of equilibrium do you have? 3. So it's impossible to find 7 unknowns using 3 equations. So it's impossible, okay, for just a student with a knowledge of structure analysis 1 to solve this problem. Draw the shear force diagram, draw the bending moment diagram, and find even the reactions here. It's impossible, okay? The only way you can solve this is by what you're going to learn and started learning in structure analysis 2, okay? So you can solve, okay, this problem and find the shear force diagram, the bending moment diagram, the reactions using the slope deflection method, okay? So that's what we're going to do now. So the solution here, I just want you to tell me, what should we do? Do you know what should we do? Just follow the steps that we wrote. So the first step, break the beam down into individual members. How many members we're going to have here? 2 members, okay? So that is member AB and member BC. So here we have member AB. What's the length of member AB? 8 meters. And what's the length of member BC? 6 meters. So they don't have the same length. Each member has a different length, okay? What are the loads on member AB? Nothing, okay? The member loading is 0. There is no member loads here on member AB. Member BC, there is a triangular load applied on it. 6 kilonewtons per meter. EI is the same for both members, okay? So the first step, what did we mention in the first step? Can you read again? What did we write about the first step? Break down the beam or the structure into individual member. Is that it?
Find the degrees of freedom.
And find the degrees of freedom. Okay? What are the degrees of freedom? They are the displacements and the rotations at the end of each member. Last time we took many examples on finding the kinematic degrees of freedom. Okay? So now what we did in the previous example, we're just going to do it in this step. What are the kinematic degrees of freedom? Just go point by point in each member. Point A. Theta and delta. How much is theta at point A? How much is delta at point A? 0. Both are 0. So theta A is 0. Delta A is 0. What about point B? How much is theta B? Unknown. I don't know how much is theta B. It has a value, but I don't know how much is that. How about delta B? 0. So now, for member AB, is there a delta? Would member AB move like this and like this? Would it have any delta in it? No, delta is 0. So delta here in this member is 0 because point A and point B both are not allowed to move vertically. Okay? And now let's do the same in member BC. At point B, is there a theta B? How much is it? Equal the same value that we had over here. Okay? So it's not a new unknown. Okay, I'm not gonna put, question mark here, It's not a new unknown. It's the same unknown, the same theta B in member AB. It has the same value in member BC. That's what the rules that we wrote, the 3 rules that we wrote about finding the kinematic degrees of freedom. It's a rigid connection between member AB and BC, so the same theta. What about delta B? 0. Okay, what about point C? How much is theta C? Why?
It's fixed in.
Because it's fixed. Delta C? 0. So what are the kinematic degrees of freedom? The total kinematic degrees of freedom. How many unknowns do we have here? Just one. What is that? Theta b. So the kinematic degrees of freedom is theta b. This is the only unknown. Everything else is known, right? Everything else is what? 0, right? We know it, it's 0. So that's the first step, okay? What's the second step? Write the slope deflection equations at the end of each member. When you see the slope deflection equation, it has a term that is the fixed end moments, right? So now let's write the fixed end moments first. Let's find the fixed end moments. So here we have two members. Member A, B, and B, C. Let's find the fixed end moments for each of those members. Member BC, we had a triangular load of 40 kilonewtons per meter. The length of that member is 6 meters. Member AB, the length was 8 meters. Now we want to find the fixed end moment at each end here. How much is that fixed end moment? And how much is that fixed end moment? I'm going to call those fixed end moment AB. And I'm going to call this, what would you call this fixed end moment? BA. Here also I need to find the fixed end moment. What would you call this one? BC. And fixed end moment at this end, what would you call this? CB. CB. So how much is the fixed end moment AB? You have a member AB with no loads on it. How much is the fixed end moment for a member with no loads? 0. Nothing. Okay? So the fixed end moment here is 0. The moments due to the applied loads is 0. There is no loads. Okay? What about the fixed end moments for the triangular load? Did we derive this? No, we didn't. But you don't need to derive it. How much is the fixed end moments for a triangular load? Just open the back of your book. You don't know it. Just open the back of your book and let me know how much are those.
Squared over 20 and 30.
Okay, so here, how much is this end?
That would be over 30.
Over 30. Okay? This is W L squared divided by 30. And the other one, the other end, it's over 20. Okay? Are those directions the same as you have in your at the back of your book? Yes. Okay? So now, how much is W? W.
Changes.
Just look at your book. How much is W?
What? Up there is 40 and at the bottom would it be 0?
Yeah. So W represents the highest, peak of the triangle here. So it's 40 kilonewtons per meter. How much is L? How much is the length of that member?
Where are you getting 40 from?
Hmm?
Where are you getting 40 from? Where are you getting 40 from?
The height, the intensity of the loads.
I thought it was 6.
Hmm?
Should be 6, right?
Oh, okay. This is 6. Okay. 6 kilonewtons per meter. Okay.
Is it 6 even on the bottom of the triangle? If you're on the left side where there's technically no height, it's still 6.
No, the thing is, no. W is the height of the triangle. Whether you apply it here or here, it's W, the triangle. Okay. So 6 kilonewtons meter multiplied by L squared. How much is L? 6 meters squared divided by 30. So the fixed end moment here is 7.2 kilonewtons meter. And that's the direction of it. Okay? from the back of your book, I just used the direction that is given at the back of the book. This is the direction of the fixed end moment. If you have a moment that is in this direction, in the slope deflection method, would that be positive or negative?
Negative.
We said clockwise is positive, counterclockwise is negative. This one is counterclockwise, so this is negative. Okay? What about the other end? W, it's 6 multiplied by L, which is 6 squared, divided by 20. So this is 10.8 kilonewton meter. Is it positive or negative? It's clockwise. Clockwise is positive. In the slope deflection, when you use the slope deflection equations, clockwise is positive, counterclockwise is negative. So this one is positive here. Okay? So now we found the slope deflection equation. Why did I do this? Because the second step, I need to write the slope deflection equations at the end of each member, and that includes, okay, or has a term that is the fixed end moment. So I'm calculating the fixed end moments to write it in the slope deflection equation. Okay? So now let's write the slope deflection equations. So again, please read the second step for me. What did we write about the second step? For the two ends of each member. How many members do we have in this equation, in this problem? 2. You have to write the slope deflection equation at each end of each member, okay? At the two ends. So how many times are you going to write the slope deflection equation? 4 times, okay? So that will give you, I have to write it here, then here, then here, then. Okay? When I write it here, it will give me M, A, B. When I write it here, it's going to give me the moment at point B. Remember BA, so I'm going to name this MBA, and then MBC, and then MCB. Okay? So let's write the equation here 4 times. The slope deflection equation 4 times. 2 times for member AB, so let's start with member AB. I'm going to write it at the left end of member AB. So how to write it? Just 4 EI divided by L, right? Multiplied by theta A plus 2 EI divided by L, theta B minus 6 EI divided by L square delta plus fixed end moment AB. Let's see here. How much is theta A? 0. So the first term is 0. How much is EI? It's just a constant, right? In the problem it was given as a constant, 2 EI divided by L. How much is L? L, no, not 6. I'm applying it on member AB, so L is the length of member AB. Okay? I'm studying member AB, so L is the length of AB, so this is 8 meters. How much is theta B? Unknown, so I'll just leave it as theta B. Minus 6 EI divided by L squared delta. What's delta?
0.
Delta is the differential deflection between point A and B, which is 0. So this term is 0. How much is the fixed end moment AB? 0. So simply here, MAB, the moment at point A, is EI divided by 4 multiplied by theta B. Just going to name this equation 1. Okay? Why? Because we cannot use this equation without knowing how much is theta B. I need to know how much is theta B. Once I know how much is theta B, I can find the moment at point A. Right? Now, let's write the equation, the slope deflection equation, at the right side of member AB, which is MBA, the moment at point B. How much is that? 4EI divided by L multiplied by theta B. I'm writing the equation at point B, so it's 4EI divided by L multiplied by theta B. Plus 2EI divided by L multiplied by theta at the other end of the member, theta A, minus 6EI divided by L squared, delta, plus the fixed end moment, BA. I'm writing it at point B, that side of the member. So 4EI divided by L, how much is L? 8. So here we have EI divided by 2, theta B. How much is theta A? 0. How much is delta? How much is the fixed end moment? 0. So here we have 2EI divided by 2, theta B. Again, still I don't know how much is theta B, so I'm just going to name this equation 2. Okay? So right now I just used the slope deflection equation twice. I still need to write it again for member BC. Member BC. The two ends of member BC. So that's going to be MBC. So how to write it for that end? 4EI divided by L, theta B, plus 2EI divided by L, theta C, not theta A. There is no A here. The two ends of the member are B and C, minus 6EI divided by L squared, delta, plus the fixed end moment BC. So 4EI divided by L, how much is L? 6. So 4EI divided by 6, the length of member BC, theta B. It's unknown, so just leave it as is. 2EI divided by L theta C, how much is theta C? How much is theta C? 0. Delta, 6EI divided by L squared delta, how much is delta? 0. There is no differential deflection between point B and point C. Plus the fixed end moment BC. How much is the fixed end moment BC? Negative 7.2. So now MBC is 2EI divided by 3 theta B minus 7.2, and still we need to find theta B. So I'm just going to name this equation 3. Okay? And then I'm going to write the equation, the slope deflection equation at the other end of the beam, MCB, the other end of the member, MCB. So that's what? CB. So 4EI divided by L multiplied by theta C plus 2EI divided by L theta B minus 6 EI divided by L squared delta plus the fixed end moment CB. How much is theta C? 0. How much is L? 6. How much is theta B? Unknown. How much is delta? 0. How much is the fixed end moment CB? 10.8. Positive or negative? Positive. So MCB is EI divided by 3 theta B plus 10.8. That's equation 4. So as you see here, the 4 moments, the moments at the end of each member, I can easily find them just if I know how much is theta B. Right? That's the problem. I need to find how much is theta B now. Okay? So now we just finished step 2, right? What's step 3? So right now we need to find theta b, okay? Through step 2. So what we need to do here is finding theta b through some equations of equilibrium. So the equation of equilibrium. Okay? How many unknowns do you need to find? 1, which is theta b. So how many equations do you need to find one unknown? Just one equation, okay? Just one equation. That one equation has to have theta b in it, okay? To find that theta b, okay? So now, our problem, we divided our problem into 2 beams like this, or 2 members. Member AB and member BC, right? There is a moment here that is called MAB, right? And there is a moment here that is called MBA. There is a moment here that's called MBC, and there is a moment here that's called MCB, right? Are those 2 members broken like this, or in the real problem they were connected together? They were connected together. So from the equilibrium, for every action there is a reaction equal in magnitude and opposite in direction. So what do you know from this? That this moment has to be equal to this moment in opposite in direction, right? So if we say equal in magnitude and opposite in direction, that means that the summation of them is equal to 0. So that's the equation of equilibrium that we're going to use here. Okay? MBA and MBC, I know that they have to be equal in magnitude and opposite in direction. So MBA plus MBC has to be equal to 0. You agree with this? Okay? So will it always be like this? It's so easy, okay? I will give you a very, very nice tip, okay? The equation of equilibrium that you're gonna have, okay? It looks so similar to the unknown. What do I mean by this? So in this problem, for example, the unknown was theta b, right? So here, blindly, I can say that the equation of equilibrium the unknown is theta. Theta is a rotation, right? The force that is related to the rotation is m. It's at point B, so mb, and just write the summation of the moments at point B is equal to 0. What are the moments at point B? It's MBA and MBC. So that's the equation that we have here. The summation of the moments at point B is equal to 0. Okay? This is how it's going to look like. Okay? It's related. If the equation of equilibrium that you're going to need to use, it's related. It looks so similar to the unknown that you have. Okay? So now, what are those moments? When I say the summation of the moments, those are MBA and MBC. Those are the moments at point B. So now, how much is MBA? Do you know how much is MBA? Do you know how much is MBC? How much is MBA? No.
Oh no, that's the 16.
How much is MBA? It's here from equation 2. It's EI divided by 2 theta b. Right? So let's just copy it from here. 2 EI, sorry, EI divided by 2 theta b. This is from equation 2. Okay? And how much is MBC?
2EI over 3 theta b minus symbol.
2EI divided by 3 theta b minus 7.2. This is from equation 3. And those has to be Summation of the MBA, MBC has to be 0. As you see now, we have one equation in theta b, right? So I'm just going to solve this equation and find how much is theta b. So solving this equation, I can find how much is theta b. As you see, there is EI here, so I'm just going to find theta b in terms of EI. So it's going to be 6.17 divided by EI, which is some constant value. Okay? So now this is theta b. I just solved my problem, right? I needed to know how much is theta b, okay, to find the n moments. Now I found how much is theta b. What would you do with this theta b? Step 4, okay? What's step 4? Substitute that back into the equation, the slope deflection equations to find the n moments, okay? So we're gonna go step 4 here, substitute back into the slope deflection equations. So substitute the value of theta b into equations 1 to 4. So equation 1 was what? MAB was equal to EI divided by 4 multiplied by theta b, right? How much is theta b? You have it now. You know how much is theta b right now, right? It's 6.17 divided by EI. So the EI cancels with the EI, so it's 6.17 divided by 4. 1.54 kilonewtons meter. That's MAB. What about MBA? That's equation 2. I'm substituting in equation 2. It was EI divided by 2 multiplied by theta b, which is 6.17 divided by EI. So this is 3.09 kilonewtons meter. And then equation 3, MBC. It's 2EI divided by 3 theta b. Now I know theta b, 6.17 divided by EI minus 7.2. So that's negative 3.09 kilonewtons meter. And then MCB, it was EI divided by 3 theta b, which is known now, plus 10.8. So that's 12.86 kilonewton meters. So those are the values, the magnitude of the moments, okay, at the end of each member, okay? Now I know how much is the magnitude. So this is member AB. How much was MAB now? How much is MAB? 1.54. I just find the value here. 1.54. Okay? Positive 1.54. That's what I got from substituting to the equation. What does positive mean? What does positive mean? No. Clockwise. Okay? It's clockwise. So here I have a moment of 1.54 kilonewtons meter. We're saying our assumption was correct. We didn't assume anything here. Okay? We didn't assume anything so far. So it's 1.54 kilonewtons meter. Okay? MBA, the moment at the other end of that member. MBA, how much is that? 3.09. Positive 3.09. What does positive 3.09? What does positive mean? Clockwise. So it's like this. 3.09 kilonewtons meter. The other member here, BC. Member AB was 8 meters long. Member BC was 8 meters long. MBC, how much is MBC?
BC is 6.
6, yes. How much is MBC? Negative 3.09. What does negative mean? Counterclockwise. So this is counterclockwise. 3.09 kilonewtons meter. How much is MCB? 12.86. Positive 12.86. So it's clockwise. 12.86 kilonewtons meter. On member BC, there was a triangular load like this, and the intensity here was 6 kilonewtons per meter. Yes?
Even though the arrow specifies whether it's positive or negative, can we put the negative sign anyways? Is that going to be wrong anyway? Like on the 3.09, you have it going counterclockwise, which is negative. But
Yes.
Can we put the negative sign on there anyways? Let's see you didn't.
No, just put it, just like the negative sign, just put it in the negative direction. That's it.
That would be like a negative negative.
I just do it because I confuse myself.
If you want to write the negative, then you just put it in the positive direction, okay? So that, you know, if you put negative here and you put it in this direction, it means the negative, it means it's the opposite direction of what you're drawing, so it means that it's positive then. So that's going to be wrong, okay? So now, we have those members, okay? I broke my beam into two members, and that was the value of the moments that should be there on each member, okay? On each of those members, there are also a vertical force, right? There is a vertical force here, and there should be a vertical force here, and there should be a vertical force here, and the vertical force here. Where do those vertical forces come from? The reactions, right? The supports. There was a support here. This is the reaction. There was a fixed support. This is the moment of the fixed support, the fixation, and there is a vertical reaction as well. There was a support here at point B, a roller support. It has a reaction. That reaction split between the two parts. Here there was a support, a fixed support. So this is the vertical reaction of the fixed support, and this is the moment reaction of the fixed support. Okay? As you see here, those two moments, if you add them together, it's what? 0. Because there was the roller support here doesn't give you a moment, so it's 0. So right now, okay, if I just need to draw the bending moment diagram, I can do so, right? I can draw the bending moment diagram without finding the magnitude of those vertical forces. Let's do this. Let's draw the bending moment diagram, okay? So this is the beam here, A, B, C. What I'm trying to do now is draw the bending moment diagram. So to draw the bending moment diagram, now that's the tricky part. Okay? I want you to forget everything about the slope deflection method. I don't need the slope deflection method anymore, right? I already know the moments at the point. I use the slope deflection method to find what I need to know. Okay? Now I'm just gonna, revert my mind to what we learned in structural analysis 1. How to draw the bending moment diagram. You need to find the moment at the critical points, right? What are the critical points here?
A, B, C.
A, B, C. How much is the moment at point A? 1.54. Is that positive or negative? Positive. Okay. So I'm just going to draw here, point A, positive 1.54 kilonewtons meter. And now, how much is the moment at point B? The critical points. And we're calculating the moment at the critical points. How to calculate the moment at the critical points? Break the beam into two halves, right? At point B. We already broke it. It's already broken, right? To two parts. And then find the moment here at point B, either from the left or from the right. How much is MB? 3.09. It's not 0. I'm not adding those together. Okay? I break the beam. It's already broken now. And then I find it either from studying the equilibrium of the left part or the right part. Right? So MB is 3.09. Is it positive or negative 3.09? Positive? Negative?
Both.
Okay. What does the slope deflection equation say? Positive is clockwise, negative is counterclockwise, right? But what did I just tell you? Forget the slope deflection method, okay? The sign rules for the slope deflection method is only for the slope deflection method. Now, you revert back to the signs of what you learned in structure analysis 1. You need to draw a bending moment diagram. If the moment is going downwards in this direction, that's negative. That's what you learned in structure analysis 1. Okay? This moment, either this one or this one, both are negative moments. Okay? So MB is negative 3.09.
Even though we're putting it back as one member.
Okay, so when you put it back as one member, it's going to be 0. Adding them together, it's 0. There was no moment applied at this point. But when you break it, this is the internal moment, the internal forces, right? You only see the internal forces when you break the member. Right?
So on the bending moment diagram, we're putting it back together.
Yeah.
It can be 0.
No. The thing is, okay, the bending moment diagram, okay, let's say, when I ask you, how much is the moment at this point? There is no moment at this point applied. There is no applied moment here, right? The moment is 0. But when you break it, there will be 2 moments, equal and opposite in magnitude. That's the magnitude of the bending moment diagram. It only appears when you break it, right? So it's negative 3.09. MB here is negative 3.09. So I just come here. Sorry, this was positive 1.54 kilonewtons meter. And now this is negative 3.09 kilonewtons meter. How much is the moment at point C? Positive or negative? Negative. Okay? Negative 12.86. So I'm just going to come here. .86 kilonewtons meter. So to draw the bending moment diagram, you need to find the moment at the critical points, plot them, and then what do you do to complete this bending moment diagram? Connect those critical values with either straight lines or curves based on the loads that you have. From point A to point B, did you have any loads? No. So that means that you're going to connect them by straight line. Right? And then from point B to point C, did you have any distributed loads? Yes, you have a triangular load, so you have a parabola here. The distributed load is on the top of the member, so you connect both points by a dotted line, and then here, okay, you're gonna have, if you remember this, if you don't, no problem, okay, I'm not gonna, then you're gonna have a curve here, okay. This curve here, if you go back to structure analysis 1, from the peak, from the base of the triangle, you go by distance L divided by square root 3, and this height is WL squared divided by 9 square root 3. If you don't remember that, no problem, just draw the curve and that's it, okay? And this is the bending moment diagram for this beam. The hatching, as we did in structure analysis 1, the signs positive and negative, and that's the bending moment diagram that we have for this beam. Okay? Yes?
So, from the start of the line that you connected from the B and C, you went L over the square root of 3 from there to get to the
to that point, and then from the dotted line you go up WL squared divided by 9 square root 3. If that was a uniform load, for example, you would go to the middle of that line, and then you go up by WL squared divided by 8. Okay? So that's now the, the bending moment diagram for that beam. We need to draw the shear force diagram for the beam. How to draw the shear force diagram? To draw the shear force diagram, as you know in structural analysis 1, you need to go up and down with the vertical forces, right? So this is where you need those vertical forces. If you need to draw the shear force diagram, you need to calculate those forces. Okay? How to calculate those forces? This is AY. This was the reaction at point A. So I'm going to name this AY. Here, this is B, okay? Or Y, the vertical force. Remember BA, point B. This is Y, BC, and this is CY. Why didn't I write BY here? Because this is not BY and this is not BY. The summation of those two forces is BY. Okay? BY is split over the both members. So BY is equal to YBA plus YBC. It's split over the two members. Okay? So how to find those forces? How to find all those forces? AY, YBA, YBC, CY. The equations of equilibrium. Apply the equations of equilibrium. For the equation of the equilibrium of this number, AB, let's take the summation of the moments about point B. So the summation here, equilibrium, what I'm doing here, applying the equilibrium, applying the equations of equilibrium of member AB, the summation of the moments about point B is equal to 0. Okay? So we have, taking the summation of the moment here, let's say clockwise is counterclockwise is positive, so we have negative 1.54, negative 3.09, plus AY times 8 equal to 0. Right? I'm taking moment about this point here. The moment of YBA about point B is 0. This moment is 3.09, negative 3.09. This moment is negative 1.54. And then AY times 8. Right? That's equal to 0. So from this equation, I can find AY. So AY is 0.579 kilonewtons. 0.579 kilonewtons. How much is YBA? It was positive. AY was positive. That means that my assumption was correct. Okay, I assumed it's going downwards, so that's correct. Now the summation of the forces in the y direction is equal to 0. How much would YBA be? 0.579 kilonewtons meter, right? There are no forces. Those two forces, AY and YBA, should be equal in opposite in direction, as I assume they are opposite in direction. I find this one 0.579, so this is 0.579, but it's upwards as I assumed. Okay? So this is 0.579. And now, I'm just going to apply the equations of equilibrium of member BC. Applying the equations of equilibrium of member BC. The same thing, I'm going to do the same thing. The summation of the moments at point B, about point B, is equal to 0. So I have 3.09 minus 12.86 plus, so this is plus CY multiplied by 6, right? Anything left here? What?
The triangular load.
The triangular load. So I need to find the effect of the triangular load. How much is the equivalent force here to this triangular load?
1/2 P.
So this is 18 kilonewtons. Okay? So I have to multiply this 16 kilonewtons, okay, by its distance. 6 times 6, sorry, 18, yeah. So I have to multiply this 18 kilonewtons by its distance. So here we have negative 18 kilonewtons by its distance to point B. How much is that distance? 2/3 L, which is 4 meters. And that is equal to 0. So from this equation, you can go ahead and find Cy, so it's going to be 13.63 kilonewtons. 13.63 kilonewtons. So now, I need to find YBC. The summation of the forces in the y direction is equal to 0. So here we have YBC. What are the forces in the y direction? YBC is going upwards, and then what else? The 18 kilonewtons. This 18 kilonewtons is going down. Okay? So I have negative 18 plus Cy. Negative 18 kilonewtons plus Cy, which is 13.63 kilonewtons. So those are equal to 0. So YBC is equal to 4.37 kilonewtons. So now I found all those vertical forces. What should I do with those vertical forces? Use them to draw the shear force diagram. Okay? So now, to draw the shear force diagram, how would you draw the shear force diagram? Do you remember? You have to start from the left. You go down with the forces going downwards, and you go up with the forces going upwards. So I'm starting from this side, from the left side. Here we have AY going downwards, right? So I'm going to go down to 0.579. 0.579 downwards. And then from point A to point B, was there any loads that would change the magnitude of the shear? No. So the shear is going to remain constant. And then at point B, if you're in this beam, you're just going to go 0.579, so you're going to go up to 0, right? And then I'm going to start drawing the shear force diagram for the other member, this member. You start from 0 again, okay? You already reached 0. You're going to go up with YBC. How much is YBC? 4.37. So I'm just going to go up from 0 here. 4.37. And then the shear is going to change, right? Because you have triangular load, right? And then how much is you're going to go down here? Over the length from B to C. How much you're going to go down? How much the shear is going to, decrease? It's going to decrease by 18. From 4.37, you're going to go down by 18. So you're going to turn out to be negative 13.63. Just 1 second. So I'm going to go 18 down. So this is dotted line. And then I'm going to go down 18, so that's negative 13.63. And then here you have the 13.63 kilonewtons meter. Okay? you have a question.
Why did we go down on the 0.57?
Here? Because you had a force that is going downwards. And the magnitude of that force was 0.579. So to draw the shear force diagram, you start from the left of the beam. You go with the direction of the force. The force was going down, so the shear is going to go down. Okay? If the force was going up, the shear will go up. Okay? So now, the shear force diagram from point B to point C, would it like change, suddenly at this point like this? No, you have a distributed load, right? If it's uniformly distributed load, that means that the shear is going to change linearly, right? But here you don't have a uniformly distributed load, you have a triangular load. So what does this mean? How would the shear change? It's a curve, okay? If you have a triangular load, so the shear is going to change as a curve. So to draw this curve, the slope of that curve is equal to the magnitude of the intensity of the load. The intensity of the triangular load at point B was how much? 0. So the slope here is 0. And then it's going to go like this down. So this is the shear force diagram. All that is left is just hatching, the sign, and this is how the shear force diagram looks like. So here I'm just gonna go back and try to make those two figures, okay, match together. What's the two figures? The bending moment diagram and the shear force diagram. Here I have this figure like this, okay? This point is where the shear is equal to 0, right? So at this point, the moment should be the maximum value, right? When the shear is equal to 0. So here, V is equal to 0. So I'm just going to go up here, and I know that at this point, the moment should be maximum. So I'm just going to go ahead and try to fix this curve. It's going to look like this. So this here, just 1 second, is M maximum. You can calculate it, or you can just, show that the maximum bending moment is going to be at that point. Yes?
How did you get the WL squared over 9 square root 3 again?
WL squared divided by 9 square root 3?
Yeah, how'd you get that?
I just memorize it.
Okay.
If you memorize it, that's fine. If not, it's from structure analysis 1. For a triangular load, the value, from the base of the triangle at the length of L divided by square root 3, it's WL squared divided by 9 square root 3. If you memorize that, that's fine. If not, I don't ask you to memorize it, okay? The only thing that I ask you to memorize it is the WL squared divided by 8 for a uniform load, okay? So this is the shear force diagram. And the bending moment diagram, I just need to fix this here now. The hatching would look like this. This is positive, and this is negative. Any question? So those are the steps of the slope deflection equation. We use those steps, those 4 steps. Again, they are so simple steps. First, break down your structure into the individual members. Find the kinematic degrees of freedom. The second step, write the slope deflection equations at the end of the 2 ends of each member. Okay? To do this, you need first to find the fixed end moments. Those can be found from the back of your book. Okay? And then, after writing the slope deflection equations, you need an equation of equilibrium or some equations of equilibrium to find the unknown kinematic degrees of freedom. Okay? And then once you find it from the equation of equilibrium, you substitute back into the slope deflection equation. You find the moments at the ends. You apply the equation of equilibrium to find the vertical forces if you need to draw the shear force diagram. And you can draw the shear force diagram, the bending moment diagram for your view. Any question? Yes?
Is there a reason why we did the bending moment first, or does it matter?
It doesn't matter. Usually people draw the shear force diagram first and then the bending moment diagram, okay? But here I just wanted to illustrate to you that you can draw the bending moment diagram without knowing those vertical forces, right? There is no relation between the vertical forces, just finding the moments, you can draw the bending moment diagram. So let's say on the homework or the exam, I just ask you to draw the bending moment diagram. You don't need to find the value of the vertical forces, okay? You just need this if you need to draw the shear force diagram. Yes?
Whenever you're using the equation of equilibrium to find your forces in the y direction,
Yes.
were you just assuming you're positive and negative on the moments?
Yeah.
You just assume it?
Yeah,
No
just
rules?
assume, yeah.
Like,
Just assume anything, and then after that, you also assume the vertical forces. So if you get positive sign for those vertical forces, your assumption was correct. If it's negative, then your assumption was wrong. Any question? Okay, so we just have 8 minutes now, or 7 minutes, okay? I just want to use those 7 minutes to discuss the first homework that you have, okay? About the steel pitch competition, okay? All I need you to do, okay, is you, I don't remember the day that I assigned, I guess 11th, okay? So around 1 week from now, okay? Actually, exactly 1 week from now. So all you need to do is read the steel pitch competition. I posted them on Blackboard. I made on the content folder on Blackboard. There is a folder that is called the steel pitch competition. You have the first assignment and you have the rules over there. It's like around 40 pages. Many pages there, you can skip them, okay? But you don't know what pages to skip, so you're gonna need to read the entire thing, okay? But it's easy to read, okay? You're just gonna read that. I need you, actually the first assignment is mainly to summarize this in a certain way. What do I need you to write? I need you to write a report that gives me mainly two basic things. What are the constraints, okay, on building this pitch? Okay, so you have to build a pitch. What are the constraints? There are constraints over the length, okay, the dimensions of that pitch. Like some dimensions, there is a range for them, okay? That's the range for the length, for example, okay? You cannot exceed that certain length. That's a constraint. The length cannot be more than this, okay? The dimensions have to fit within those dimensions. So I need you to write all the constraints regarding the dimensions, regarding the weights. So the weight of your structure, there is a limitation for the weights, okay? There is some constraints regarding the deflection, okay? When you load the bridge, okay? There will be some deflections. Those deflections can be any value, but they cannot exceed a certain limit. That's the constraint, okay? So there is constraints for the deflection, okay? There is constraints for you're gonna build this bridge out of individual members, okay? There is some constraints over the length of those individual members. There is some constraints over the time of building that bridge, okay? If you exceed a certain time, you're eliminated from the competition, okay? So that's a constraint, okay? So you need to find or summarize those constraints. That's one thing. The second thing is the weighting criteria. Like, for example, the time. You can build this bridge in 10 minutes or 15 minutes, 20 minutes. You cannot exceed a certain limit. That's the constraint. But as long as you're within the limit, okay? The shorter time that you're going to use, the better score you're going to get, okay? So I need you to tell me, what's the weighting criteria for the time, okay? What's the relation between the time and the score that you're going to get, okay? You need to find this from reading the rules, okay? The weighting criteria regarding the deflection. How is the deflection going to be weighted, okay? The equation that is going to be used to find to weight the deflection. The smaller the deflection is, the better score you're going to get. What's the equation that is used to find this score, okay? What would the name of this score be, okay? The construction time, the deflection, the weight, okay? The weighting criteria for the weight. So I need you to find all those things, okay? certainly you're going to need to write first an introduction, okay? And then also, when you find the deflection, you're going to find the deflection based on the loading on the bridge. What is the loading according to the rules, okay? The rules are going to assign the loads that are going to be, applied on this bridge. What are the loads, okay? So I need you to define what are the loads, how they're going to be assigned or chosen, okay? Because there are many different loads and only one of them are going to be chosen on the competition, okay? So I need you to know what are the loads, okay? Write this in your summary. So those are the things that mainly I need you to write to find on the summary. The definition of the loads, where like the deflection, where would the deflection be measured, okay? Is it in the middle? Where exactly? You need to find this from reading the rules, okay? Where will the deflection be measured, okay? The constraints, the weighting criteria, and you can copy images or drawings from the rules and put it in your report if you need this. I believe you're going to need this, okay? So you can copy from that. I don't want a long report. I just want you to limit this to 3 pages, okay? Without, the drawings. The drawings can be beyond this 3 pages limit, okay? But don't go beyond 3 pages. If you want to go less than 3 pages, that's fine, okay? But don't go beyond 3 pages, okay? And I need you to write all the details that I mentioned, okay? Constraints, weighting criteria, the load definition, the deflection definition, all those things, okay? Any question? Okay, so if you have any questions, please let me know. Those are individual reports, okay? Each one has to write his own report, okay? It has to be typed, okay?
I just have a question. Are we just using the engineering tool standards for
You too?